take out a good bulk of the material, and dewatering. The pump, the sump, and the cyclone were a supplement and overall used to increase the yield. So along the ways, decided to, the next step for the process was we needed a drier material coming off of the entire process. Screw could only get it so far. Getting onto a conveyor belt, there was still some loose water on there. Could cause housekeeping issues. By adding a dewatering screen, it removed all of the freestanding water, produced a drip-free product. Conveyor belts were able to work that handle that better. The stockpiles would, be drier at that point right there. Material was essentially ready to go, shipped out that day if needed be. Had a faster turnaround for the overall product. So when demands for the sand became higher and higher, needing a drier and drier stockpile, that's why the dewatering screens were introduced. And at the same time, the cyclones were still doing the majority of the final classification. So at that point, there was a question whether the screw should be in the process, and it was removed. And the change in that entire process, when you remove the screw, that was doing a bulk load relief for the cyclone. So the pump, the sump, and the cyclone had to get bigger because there wasn't that load relief from the screw. Everything else was still staying the same. The cyclone overflow was still the waste. So the cyclone was doing all of the process. The dewatering screen's doing all of the dewatering. The sizing screen up front really hadn't changed too much. So that's where we moved into the modern sand plant. So that's when we say modern sand plants for the washing and classifying and dewatering of sand, drip-free consistency. And when I say drip-free consistency, just imagine taking a handful of sand, making a ball, kind of like a snowball, and pressing it together and trying to squeeze the water out. No water would come out. That's the drip-free aspect of it. So these kind of plants are modular in design. They're easy to set up, small footprint, and there's a level of configurability to them for the different applications that you want to do. So a little more flexibility. It does take a little bit of planning. Just to take a look at it, the next slide that we're going to be looking at is one of the case studies that we've done.
Okay, yeah, looking here. So this is a project that we did in Kermit, Texas with our dealer Excel Machinery. Their goal with this project was making 140 mesh frac sand. So they needed something that was easy to set up, that had they had a small window to make this thing produce material. So we wanted to find some equipment that could produce it efficiently and cost effective at a good price point. And their whole goal was really just to get those ultrafines out of there so they could have a sellable product. Also, I want to mention too, we do have notes on here in the chat. If you have any questions as we're going along, make sure you put those in there and we'll address them as we go. So our dealer Excel, they came up with a Falcon 724 for this application. They would be good for the tonnage they were looking to do. We rate these plants anywhere between 300 and 350 tons an hour. And this application, they were more around the 270 tons per hour in the production in the real world, making sure that they could make the classification and the cleanliness of the material needed in order to sell it. They really liked this one because of its ease of being able to set it up. They were able to put this plant up in about 2 days. It is a modular type design. So we have a sump, a dewatering screen that sets on top of that, and a cyclone bank that goes on top of those two items. So very modular, very easy to put together. It comes with its own power panel, and then everything on the plant is mirrored. So if you need to have your feed come into the left or right side of the sump, or if you need to move your catwalks from either side, that is all available as well. And they had this thing actually producing material in under 2 weeks. Again, like Alan said, a big key here was the moisture content. So they were able to get to about 7 to 8% moisture off of that dewatering screen. And the footprint was much smaller than what they were used to, so that did help. at the end of the day, I mean, they were very happy. They had a nice dry product that was in spec, and they were able to load it out and sell it within the same day as it coming off of this plant. So that plant was put out there in April of 2024. It's been running almost continuously since, and a very good case study for Eagle and our dealer Excel.
So just to give a little more of a breakdown of what a plant looks like, Kurt gave an excellent verbal reference of it, but here's a picture of it. You know, you have the sidewalk. We talked about that as being configurable. That's the reversible. The access is very important to these type of plants because they're a little bit more elevated, a little bit harder to look at from the ground level. So you need to get up on that level, looking at the screen itself, looking at the underflow of the cyclone. That's what the walkway presents access to. You know, the control panel, then we have the slurry pump, which is, just think of it as a conveyor for slurry, and that's taking it up to the cyclones. Cyclones are doing its classification. The overflow is taken away, and the dewatering screen has that discharge of material. So how a sand plant works, you know, we've kind of talked about this a little bit. Most of these sand plants like this are sump receiving the slurry in the first place. The pump takes it up to the cyclones. Sand is classified there. The dewatering, like I said, is a drip-free, ready for conveying. Video here shows how it's discharging. So you see how that material just kind of crumbles off the end of that dewatering screen. 10% is a very normal range. There are a lot of applications where we have gotten down to the 7%. You're not going to really see much further beyond that off of the dewatering screen. Some material holds its water a little bit more, even though it's still drip-free. It can go all the way up to 20%, but it all depends on the material itself. So sizing up a sand plant, like a lot of plants, you're just looking at the tons per hour, your gallons per minute, the feed gradation. And we have it in here, product, you know, multiple products and gradations. And that's because some of these plants are not just that straightforward. They utilize the dewatering screen for two products at the same time. So you'd have parallel, you know, sump, pump, cyclones, and then have both of those systems discharge on the same dewatering screen. It's a very common aspect of some of the more advanced ones. So you can have a coarser sand and then a finer sand and a blending capability on the discharge. So that's really on the sump fed type of approach. And like I said, most of those are sump fed. More custom designs can be screen fed, just changes a little bit. Still same equipment on there, but that's the approach of most sand plants. So with the cyclone being the majority doing the heavy lifting of all the separation in here, I wanted to touch upon the little bit of the cyclone history. We talk about it as a modern piece of equipment, but in truth, it's quite old. You know, it was first patented back in 1885. They started really fine-tuning it for a liquid solid separation, 1891. For a good portion of that time, for about 50 years, it just really wasn't understood. And in truth, in some industries, it's still not really accepted or understood by most people. Both, though at this time, if you dig down into the technical aspects of it, it's pretty well understood. It's very predictable. But it was in 1939, a group called the Dutch State Mines took a chance and started utilizing hydrocyclone technology, mainly for coal and sand separation. The model that they made out of it, you know, really changed and set the standard for the rest of the industry. World War II ended, and we really needed, as a world, not just as a country, a boom in that type of material. So the cyclones themselves became more prominent because they provided an advantage that other pieces of equipment did, you know, the higher capacity aspects of it. In some industries, the cyclones have completely replaced the older technologies. And for the sand and aggregate type of approach, you know, a lot of the classic equipment is still good, but, you know, the hydrocyclones have opened up the door for other areas. So cyclone application, classifying between 38 microns, which is about 400 mesh, and 150 microns, which is about 80 mesh. Desliming the material, removing clays and ultrafines is a real good role for a cyclone. Those materials stay with the water. The water is removed into the overflow. But at fines recovery, this is an area that the cyclones really has excelled at in a lot of comparisons to other pieces of equipment. And as for thickening for downstream equipment, it really is good for water scalping in a very tight area. So it has a lot of flexibility, a lot of uses within our industry. So the advantage of the cyclone itself is it tends to be pretty expensive in comparison. Processes high volume, minimal floor space, head space, no moving parts within the cyclone. It really counts on the pump to do the majority of the heavy lifting to get this to actually perform. It does have a better separation efficiency over free settling classifiers, and the capacity is independent of the amount of fines present in the feed itself, which is different from what fine material washers have. You will get them derated if you have excessive amount of -50 mesh. So that's where the cyclone doesn't really have an impact on the gradation that's going into the unit. It still performs at the same rate. It doesn't get derated. Making up the cyclone itself, pretty simple. It's a feed box, feed inlet itself, a vortex finder that's for the overflow, an optional feed box extension, which is part of the configurability of the cyclone itself. The extension itself will cause the cyclone to capture finer material. The cone sections, it's just shown as one here, but it can have multiple sections. This is another part of the process to get the cyclone itself to perform properly. In the spigot, some refer to it as the apex. This is the discharge, the underflow. So how a cyclone actually works, since we can't see inside of it, we have to do a lot of research and modeling, and that's where it's stuck for quite a while, why it didn't get done, because people just couldn't see inside of it. They really needed confidence in how this works. So over the time, that's what's really happened. So the centrifugal shaped device has one entrance and two exits. Essentially, it's a highly engineered pipe T. And in that, it has to have certain performance requirements in order for it to start doing that separation. So it's fed under centrifuge force, causes the material to accelerate around the outside or in the unit itself. That acceleration causes material to start its separation. And also the swirling motion, kind of like a tornado, creates a vacuum in the middle, and that starts pulling air up through it. So you have two opposing flows within there. You have the slurry itself circling around, and then you have an air core being pulled up into the unit. What's happening in here is the coarse and heavy material is doing a motion downward, while the lighter, finer material is doing its motion upward. Taking a little bit different look at that, same type of idea behind it, just explaining a little bit different. The rotationary spins cause the particles to spin on the outside. The heavier the particles, the more it gets pushed to the outside. You recover the particles as it discharges out of the underflow. The reverse of there causes a bulk of the liquid and some of the fines to go with the air core that's followed up through the vortex finder. That's where the light fraction happens. So there's that swirling motion of both of them, the air core and the slurry itself. And really, to get more into the physics side of it, what's happening in there is you have two different opposing forces pulling on a particle in different directions. The centrifuge forces caused by the pressure of going into this unit pull the material to the outside. The larger the particle, the heavier particle, the more the centrifuge force has an impact on it. So that particle takes a look at it, and the centrifuge forces are greater than the drag forces, it's going to go into the underflow because it's going to be pinned to the outside. If the centrifuge forces are less than the drag forces, meaning the particle is smaller, lighter, goes with the water, it has a higher probability of going into the overflow. So cyclone performance is really measured by measuring the pressure, because the pressure is a great way of telling us how much centrifugal force indirectly is being caused within the unit. So the higher the pressure, the higher the centrifugal force. The lower the pressure, the lower centrifugal force. So with a lower pressure, the centrifugal force has less of an impact on the particles, and the drag force will pull it more into the middle. Higher pressure, higher centrifugal forces, more pushing to the outside. So when you're operating a cyclone, you want to look at what you're really trying to do. If you're trying to make a cut, if you remember, I said it goes from 38 microns to 150 microns. So if you're trying to make that cut at 38 microns, you're going to want a very high pressure, so 20 to 25 psi. If you're going to be wanting to make a coarser cut, that's where you're going to be going with the lower pressure down in the 8 and the 10 psi. So when you're doing your sand washing, you're generally doing that at the lower pressure. When you're doing your fines recovery, you're doing it at the higher pressure. Now, the vortex finder does play an impact on the cut size. So if you have the same flow going into the unit and you change your vortex finder and you go to a larger vortex finder, you're going to make a coarser cut. And if you think of it as just an opening for the material to go through, you've opened that up, allow more material to be captured by the vortex finder. It also reduces the back pressure on the entire unit. So you'll see an inlet pressure go down. The smaller vortex finder with the same flow rate, you're going to get the finer separation because there's less room for that material to go out. So the vortex finder and the inlet pressure itself go hand in hand to help make the size cut that you're looking for. On the underflow, this is really more driven by the percent solids in the entire slurry. So it's going to come out looking kind of like an umbrella. What you're seeing here is as the slurry comes out, it'll fan out. And you can see this flexing a little bit here and there. And that's a change in the tons per hour that's going through these units. The inside of that is hollow. That's where the air core is being pulled up in. So as you have more material, that umbrella tightens up inward, becomes, the spread of it becomes less and less. As you have more water, it spreads out, fanning out more, and you'll see less of a curtain and more of water spray coming out of it. And as you increase the amount of water coming out of the bottom of the cyclone, that's where the fines will also come with. So in a way, it does have an effect on your cut size, but only for the amount of fine material that gets pulled into the underflow, which would normally end up in the overflow. If in a very proper running cyclone, the best situation is to have as tight of a underflow cone as possible, and that's where you're going to get your highest efficiency. Now, on the opposite side of that, if you get up into a position where you have too much solids, that's where you get into what's called roping. And it's called roping for a simple reason. It resembles an old rope as it's coming out, being swung at the bottom of the cyclone. So what's happening here is the feed density is too high for this configuration of the cyclone. So you have to reduce the feed density by decreasing the solids at the sump. And that may not necessarily be what you want to do, because you want to produce X amount of tons, and decrease in the throughput into the plant is detrimental. So fortunately, there's another path to go, and that means the spigot's too small, and you can replace it with a larger spigot or apex, depending on which terminology you prefer. They do have slightly different meanings, but they get interchanged quite a bit. So opening that up allows that air core to form up in there and begins that separation again. Without that type of air core, you really only have a pipe tee. That material just goes where it wants to go, and there is really no controlled separation efficiency at this point.
And also, I want to chime in on that portion. So with all of these plants, before they're sold, we have our applications and engineering group look at it to make sure that it's going to work for your application. We prefer that you send us out your material gradations, the cut that you're looking to make. There are some adjustments that we can make as far as apex, vortex finder. We do a mass balance or flow on it to see the water that's going to be necessary. There's a lot that goes into this. So a lot of times we'll get the question, can I just replace my sand screw with one of these units? And the question or the answer is yes. We just got to make sure we do our homework and make sure it's going to work properly for you, and that you have enough water and that the cyclones are set up properly. I think they get in the past, some of these units have had a bad reputation because they take a little bit of work to get them up and running properly, whereas a sand screw is kind of a little more simplistic, we'll say.
That's a very good point, Kurt. And that kind of goes back to why it was a little bit slower to accept cyclones into the industry, because it does take a little bit of more forethought when sizing these up and putting them into place. You have a screw, you can move from site to site. You really don't need to think too much about it. You move a cyclone from site to site, you need to take a look at the feed, just like Kurt says, and really understand how it's going to affect the unit. Since it's going to be higher, and the water, yes.
Yeah, the water consumption too is a big factor. So just as an example, let's say a Twin 44, which is probably one of the most standard fine material washers out there, usually at 150 mesh cut runs, about 14 to 1500 gallons per minute of water necessary. So for that tonnage and making the same cut for a Falcon or a cyclone based plant, you could be doubling that water consumption in order to make that same product and tonnage. So keep that in mind. Not all applications, but usually the water is going to increase substantially if you move to a system like this.
At the same time, you have a better control over the water itself. So there is a balancing act to that. So
correct, and a better cut.
Yeah. So as we'll get into this is why you would pick a cyclone over a fine material washer. And this segues perfectly into this idea. And, the cyclone is close to atmosphere, not necessarily an advantage, but it is close to atmosphere. You don't get to see what's happening in there. You get to see the results. We say this very fast running just means it has a higher capacity. It just handles more material in a smaller area. It just overall can increase your overall capacity of your plant. It's great at capturing fine particles. Because of the fluctuation, the centers around the apex itself, it does not like irregular feed. With the pressure being the drive of the centrifugal force issues of it, changing the flow within the cyclone changes its cut point, changes its performance. So it does not like being irregularly fed with solids or fluids. So it likes solid, stable, consistent type of process. And once it has that, it will make a very solid, predictable performance. So they go hand in hand. They don't like being overfed. That kind of goes to the apex itself. It backs up, causes a separation issue. It doesn't not handle being overfed very well. Oversized particles also have an impact on it, meaning that if you get too large of particles in there, it can damage your liners. The material discharging from the cyclone itself, it's not conveyorable. It's too wet. It's down in the 60-70% solids. You try putting that on a conveyor belt, and you're just going to have a mess. So that's one disadvantage of it, pure and simple. Sometimes it's not truly a disadvantage if you're using this further on in the process and you don't want to dewater it that much. In comparison to a fine material washer, it's open atmosphere. You can see it. You can walk by it. You can get a feel for what's going on in there. Not just the results of it, but you can see the process going on in there. But they are very slow running. The capacity can be impacted pretty severe by the amount of fine material. They do struggle to capture very fine particles. They're not recoverable of that. That goes in the overflow, along with some good material. If you're trying to focus on a certain spec and you're forcing the fine particles out, you may very well end up forcing good material out in order to meet that specification. Advantage to them is they do handle irregular feeds pretty good, because they're not under pressure. It's not the driving factor. The settling velocity is really what's happening in here. It's a free settling classifier. So moving up and down is not that big of an impact on a fine material washer in comparison to a cyclone. It can tolerate some oversized particles. Obviously, you can't go too crazy with oversized particles. It's very good at handling -3/8" material. And it does dewater a material enough to go onto a conveyor. It has been done for a number of years. The other big advantage that a screw can have is it handles very abrasive. Since it is slow moving, it doesn't have the wear rate in some cases that a cyclone can have. If you have some very abrasive material going through a cyclone, that can attack the liners. So sometimes you have to take a look at the liners of a cyclone to react to the abrasive material. But with a fine material washer, they handle that much better. So there's not really calling it advantages, disadvantages. It's just where one shines versus the other. So the pumps, they're not new. They've been around for a number of years, but they are a component that's necessary to a cyclone sand plant. As I said before, they're essentially a conveyor for slurry, and they use centrifuge forces to move the material from your sump into the pipes. And you've heard me mention centrifuge forces before. A real quick way to think of it, think back to your younger days, being on a merry-go-round. If you're on the merry-go-round, the faster it goes, the more it tries to throw you off of that merry-go-round. And that's what centrifuge forces are. As I said, it's very key in providing the slurry to a cyclone. You can run a slurry without a pump, but there are a lot of requirements you have to do in order for that to happen. You have to deliver the desired pressure at that cyclone. So it requires a lot of elevation if you're doing it by gravity. So pump just makes it a whole lot easier, more controllable. So looking at a pump component itself, they're very simple, but once again, they're kind of closed, so you don't get to see inside of them what's going on. So you have your suction inlet, your vanes, which are part of your impeller, the liners themselves, the casings, and the discharge port. All of those are required in order for this to work. So material flows into the suction eye. Calling it a suction eye is a little bit of a misnomer. It does not actually pull the material into the pump. It requires the sump and atmosphere to push slurry into the pump. Once that happens, the impeller will impart energy onto the slurry, and that's, as it's spinning around, it's throwing the material outward, causing a pressure to build up inside of the casing. So using that centrifuge force to push that out, the material doesn't have anywhere to go against the casing itself, so it increases its pressure, and then it causes it to move out the discharge port at a pressure. So as you put more energy into the pump, the further and further you can pump it against the higher heads. So there is as we were talking about for the cyclones, as we're dealing with a cyclone and you move it from site to site, if you change the process and you change the flow, you also have to change the pump. And as you change the pump, that's going to affect the cyclone. So all these are interlocked as you're going through. So if you have an application where you're doing, let's say, 2,000 gallons, and now you want to do 2,500 gallons, you're going to have to change your pump. And then you're also probably going to have to adjust your cyclone to handle the higher flow rate. And they are configurable in that regard. So anytime that you're moving any of these plants around or anything like that, changing the process, it's a real good idea to pull in the original manufacturer and talk to them about it so they can help you set this situation up the best that you can for you, so you get the results that you want. Moving on to the dewatering screens, they're really the tail end of it. You know, once again, they're not doing normally any type of separation on there. They're producing a stackable, conveyable, usually ready to sell drip-free sand product as it discharges off there. Short time turnaround on a stockpile into a truck, as was mentioned earlier, as early as the very same day, but usually next day is what I see in the fields when I've been out there. So you can see this material is coming off. It's flowing pretty easy. The more it flows like this, the less it chunks up, the less water that's actually in it. So taking a look at the dewatering history, the dewatering screen is by far the newest piece of equipment in this entire process. It was originated in South Africa used for gold mining. They wanted to dry up material with a screen, which instead of sizing. It expanded a short time later into the coal industry. It was brought into North America around 1987, and it really started being pushed not just in the US, but around the world in the early 1990s. It gets you to a point where you're drying the material to a level that it's very easy to handle. So a dewatering screen, while screens have been around for a very long time, dewatering screens, around the 50-year frame, they're designed to do the exact opposite of what traditional screens will do. It's not to make a separation like a traditional screen would do, allowing the material to pass through. It's just the opposite. It wants to retain as much material on the screen media as possible and only allow the water to pass through. Now, that being said, there are some fines that pass through. And that can actually be used to your advantage at times. And I'll talk a little bit about that as we're moving forward. So how a dewatering screen works. So you heard us say the drip-free product, drip-free sand, stackable, conveyable, ready to sell. Material comes on normally onto a dewatering screen in the 50 to 60% solids range. Underflow from a cyclone, you underflow from a screen, underflow from a sand classifying tank. A lot of products out there, piece of equipment will make about a 50 to 60% solids slurry coming there. So it fits well within what a dewatering screen can do. If you do go below the 50%, what ends up having to do is you have to oversize the dewatering screen just to handle the drainage area. These are designed to handle that specific or higher percent solids for drainage. So the pool of water will form in the back, and since the screen is on an incline, the linear motion of the motors themselves will throw the sand forward, but the water will always flow backwards. So it stays back in this pool area, and the back plane itself allows a lot of the drainage out, and it drains out in the first part of the dewatering screen itself. And as it moves up there, it gets drier and drier, and the material discharges at that drip free at the end. Because of the incline, that's why the water doesn't go up there. You can, if you're in a situation where you're feeding the dewatering screen like 70% solids and you're trying to clean it up, get rid of excessive water, just that little bit more, you can actually drop the angle down a little bit, increase the transitional speed, and you'll get a slight higher throughput on these units. Most of the units are designed to have that 5-degree incline on it to force that water pool. In situations where you don't have the water pool, you can take a little bit different of approach to it. So looking at the components of a dewatering screen, and the picture here that we're looking at is a real good setup of how a dewatering screen can be installed. The discharge chute is an optional part of it. You have to design that for your application, so it's not necessarily part of the dewatering screen package itself. It can be added on there, but really you need to look at the application and how you're discharging the material, where you're discharging it to. Are you doing it onto a transfer conveyor? or do you need a narrower chute to funnel it down into a conveyor itself? So that is something that needs to be discussed when you're looking at this. You can either build your own or have a manufacturer build it for you, but it needs to have some specifications onto it. The vibrating motors of the dewatering screen, that's doing all the action. They're linear motion. They're set at that 45-degree angle. Optional spray bars. Why would you put spray bars on a dewatering screen? Why would I add water to a dewatering screen? Well, in this application of a sand plant, by adding spray bars on there, you can actually do a secondary wash of your material. Your cyclone gets rid of the majority of your fine particles, but you're just a little bit out of spec. You have a little bit too much fines, and you do that last bit of cleanup. And by spraying water on there, you're increasing the amount of material that passes through the screen media. Now, you're not losing that material per se, especially if it's good material, because it's going down into a sump, and then that's going back through the cyclone. Now, what happens is that material that you really want to get rid of starts building up, and eventually some of it will end up in your overflow. So it does clean up that area of the fine material that will start building up in the system. And the cyclone is the relief valve for that. So that ends up in the overflow itself. So what you're doing is giving the cyclone another shot at discharging that material you don't want in there with the spray bars. Feed section, you don't normally just drop material onto a dewatering screen unless it's relatively solid to begin with, and you just do a cleanup. You can do a fine material wash or discharge straight onto a screw. Cyclones generally will have a feed box that you're going to feed into, and it'll spread the material across, because you really want all that material spread across that dewatering screen. You have the screen media itself, and you'll size the screen media depending on the application that you have, whether you're doing fine material recovery or you're doing a classification. The rubber buffers, they're really to isolate the dewatering screen because it's shaking. If you didn't have that isolated from there, you would have that vibration transferring over into your structure. So the rubber buffers are there to safeguard the structure around it and underneath it, because you are having water. You're going to need an underpan or a sump aspect of it. In these type of plants, it's a sump. In areas where you just want the underflow to go away, just in a dewatering screen application, not in a sand plant approach, you'd have an underpan and possibly just let it gravity flow away. But that's specifically for a dewatering screen. For this type of wash plant, it's going to be a sump.
And also on this slide, Alan, so what we're looking at here is one of our Eagle Dry screens. This looks like a 7x12, which is very common for us. If you notice, the back of it is flat. This one is pretty much designed to fit under a fine material washer. It doesn't have the back angled baffle plate like you would see under a cyclone-based system. Very good for dewatering after a fine material washer if you want to get your moisture content down even further. And then also we have a system where on that underpan or sump, if you're not just gravity flowing out or pumping it far away, we can pump that back to the intake feed box of the fine material washer and let it go around a second time to clean it up even more. So that is available as well.
Yeah, so dewatering screens have really added a whole new layer to sand and aggregate processing, because it brings something to the table that wasn't out there before. So it gives you some flexibility, allows you to look at the process just a little bit differently. So dewatering screen operation, just a picture of what's going on there. As you can see, the first picture there's a ton of water on this. It's just coming in there. This is probably in the 50% solid range coming into this plant. Plus the spray bars in there to clean it up a little bit. So they're having a little bit of fine material as it's going through the plant. The cyclone didn't quite get it enough. And it's no fault from the cyclone. It has to do with the feed coming in. It's just a higher amount of fines in there. So this is an approach of attacking the fines in an additional way. It's getting that secondary wash in there that really provides the fine tuning of your product. And then the discharge right here, as you can see, it's coming off there. It's clumping off. That's in the range of, I would say 10, maybe 12% solids coming off there. As you can see, there's water right towards the very end of it. That kind of indicates that the screen is close to its capacity. If you were to add a lot more tonnage to this, you might get some wet material coming off of it. You might need to do a little bit of modifications on the screen media. Towards the discharge end, you can do some opening it up and allow the water to discharge or to pass through a little bit easier while still maintaining all of that material on there. So there are some aspects that you can do right here. Another aspect you can do is possibly looking back at the cyclone itself. Maybe the spigot has worn away a little bit and it's letting a little bit too much water go down. And that means you may need to close that up a little bit, and that would really dry up the discharge. Or at this point, it's pretty dry, but you can really pull back that water that you're seeing on the discharge end of that. So the advantages of dewatering screen, it tends to be more flexible with multiple products per machine, allows that blending. That's what I was talking about. You can have the coarse sand on one side and the fine sand on the other, and then you can meter in the fine sand to make the product spec that you need to do. It definitely makes a drier product overall. It cleans up, gets you a higher SE than other processes. That's one of its advantages that you don't normally think about, but it does make a cleaner product in the end of it. And in some cases, you end up using less water, reducing overall water loss because you're keeping that water within the system itself instead of sending it off to a pond through evaporation or other aspects where you can lose that water. So it can improve your overall water balance. Because of all of that, and you take a look at the entire wash plant itself. The cyclone dewatering screen plants, they generally do have a higher average yield in the range of 3 to 5%, and that depends upon your material itself than just a screw. So if you start running the numbers on this, so you have an increased product yield of just say 5 tons per hour, $5 a ton, that's 50,000 per year on an average for 20,000 hours per year. Just where those numbers come from, a screw overflow generally has 70 to 75 minus 200 mesh in it, which means you're losing good material. On a cyclone underflow, you only have 85 to 90% minus 200 mesh, or that is minus 200 mesh, 85 to 90%. So you're only losing 15 to 10% of your good material versus 30 to 25% of your good material. So there's where your increased yield happens. So moving away from just the wash plant, still using the exact same technology, just a little bit different approach to it, you expand the entire process to use to capture some fines, the ultra fines, the stuff that it could be considered waste streams going out to a pond. And this is capturing material down to 400 mesh. And once again, like I said, it's still using the same material, just slightly different approach to it. So instead of digging out a pond, if you're in that situation, you reduce the amount of material that could go to a settling pond, decreases the clean out frequency, decreases the cost in general, reduces the load on downstream processing equipment by getting that material out here. And you may actually have a potential sellable product in multiple places. Once they had it on the ground into a stockpile, a home is found for that material. And it went from a waste and a cost to now a revenue stream, or at least a break-even stream. So when we do with cyclones for the fine recovery, there's a slightly different approach. You may have picked up on it already. We're going to be running them at a higher pressure. So we're operating in that 20 to 25 PSI. When we're classifying, we're now focusing down on that 38 microns range. It's still, thickening up the material for downstream, removing it from the process itself. When you take a look at a wash plant, you may see 1 or 2 cyclones, larger cyclones on there. When you take a look at a fines recovery plant, you're going to be looking at multiple smaller cyclones. And just a word of warning, you don't want to go too small of cyclones. The material in there is still larger than what some small cyclones can handle. You go down into the 4-inch and 6-inch cyclones, and they end up being plugged up because the top size just can't go through the bottom of the cyclone itself, and they plug up. So making sure you don't go too small of a cyclone, you're really not theoretically getting much more material by going with that small of a cyclone on there, and you're having an overall operation ease by using the appropriate size cyclone for that type of process. And that, once again, kind of goes into, hey, talk to your people, let's take samples, let's take a look at it, run it through an applications thing, and we can make that real good suggestion for you. So as I was saying, smaller diameter cyclones, they make a smaller cut. It's just the physics of it. The centrifugal forces, as you're getting smaller, become a higher impact on the material itself. More material will end up in your underflow. So larger diameter cyclones, they make a coarser or larger cut size. That's why sand plants use large cyclones. Fines recovery uses small cyclones. So, and just like the other ones, even though all of this material may pass through the screen opening, the media opening, it theoretically would pass through there. Because of the way the process is set up, the way the dewatering screens happen, the material just doesn't pass through. You start building up a bed on there, the material cakes up, blinds up the material, or blinds up the media, and that material comes across the discharge of the dewatering screen, just like on the normal wash plant. It's still drip free. Now it does have a higher amount of moisture in it because smaller particles retain more moisture. So these type of units right here, you're going to be discharging in the range of 15 to 20% solids. But if you still reach out and grab a handful of that and try to squeeze water out, it's just not going to happen. It's just because of the nature of the size of the material, it just retains a little bit more water, even though it's considered drip free. The components of the plant, pretty much the same thing. The cyclone, the dewatering screen, the sump, the pump, you're still going to want to have that access on there. The major difference that you want to do here for a fines recovery plant is as the slurry is going into the sump, the biggest difference between all of this is a lot of the cyclone overflow is fed back into the sump itself. And this is helping to maintain a steady, stable process. So the slurry pump is going at the same rate the entire time. Cyclones are operating at the same pressure all the time. The underflow from the dewatering screen is not being lost. It's going back into the process, going back up to the cyclone. So even at the very beginning of a fines recovery plant, as you're starting it up, it may seem like it's not capturing anything. It takes a while for that material to build up until it builds a cake on the dewatering screen. And then you have that discharge of that material, which ends up being drip free. So all of that, like I said, that material may be 100% passing the media opening, but eventually it will catch a bed on there and you'll start pulling out that material, and it'll consistently pull out the material as long as it's coming in there. And since the material may pass through the dewatering screen, it's just trapped in the loop. Your cyclone, just like the other wash plant, it's making that classification. If it's going to end up on that screen, majority of the time it's going to end up on that screen again. So it's that closed loop process. So just taking a look at where everything kind of fits in with equipment ranges. You have your sizing screen, which is going to be taking care of that real coarse material up front, the aggregate side. And you're really not doing a lot of screens for sand itself. That's when you're moving into the wet processing side. Haven't talked anything about, what we have listed here, FBCs or hydrosizers. Those are just names for a hindered settling classifier. not really going to get into that. That's really not used a lot in the sand and aggregate. And FBC is used in like lignite removal. If you have like any coal in your sand and you need to make a color test, that's where an FBC or a hydrosizer can come into play, because it's real good at removing that light material. The free settling classifiers is a general term, and where we fit in with free settling classifiers is a fine material washer is a free settling classifier. Sand classifying tank is one. A bucket wheel, feed regulating sumps. Those are all considered free settling classifiers because material settles in at a free rate. There's no hindered material stopping it, which is what's happening in the hydrosizer. So the fine material washers, the bucket wheels, the feed regulator sumps, they're all essentially the same thing happening. Really, the only difference is what mechanism is pulling the solids out of the tank. So in a fine material washer, you're using a screw. In a bucket wheel, you're obviously using a bucket. And with a feed regulating sump, you're using a pump to remove the solids out. But the same overflow is happening. That's where the fines are going into. That's the classification as the overflow. So one classic piece of equipment that there still is not a replacement for, and just because it just handles what it needs to do so well, is a sand classifying tank. And where we're sitting with sand classifying tank is, it originally started off, it's called the water scalping tank, because it was real good at getting the solids out, much like a feed regulating, getting rid of the water and getting the solids. Then they started noticing that you can make a separation with this. And as you're putting it in there, you can make separation from the middle of your gradation. So you can remove 30 to 100 mesh material out of the middle. So you can produce multiple specific sand recipes suited for different construction specifications, asphalt. So within this unit, you have 3 exit points: launderer 1, launderer 2, launderer 3, and an overflow. And generally speaking, you have launderer 1 and launderer 3 making a product. Launderer 2 is a waste, and an overflow is a waste. But you could actually, if you found the market for it, all 3 of those possibly could be, or all 4 of those could be a product. But it separates one stream into 4, which is unique of any type of process equipment out there.
And also with these, Alan, so the control systems, I don't think we have a slide on it, but we've come a long way. We've had controllers on these for, since the 1960s. Our newest ones are the digital dial split and the Mark 10. Both of these are very good for putting multiple recipes in. So if you're pulling from one end of the pit and you change the next week and you're doing a different product, or you have multiple products you're trying to produce, it's all controlled now with the PLC and the digital dial split. So they have also now, with the capabilities, if you have Ethernet, we can remote into the system. We also use AT&T Cellular and most recently Starlink. So if you have any issues, our folks back at the factory can remote into your system and help you troubleshoot. So as far as technology goes, they've come a long way.
Yeah, I was on site when I think we first used the Starlink for the very first time. The site provided it, and I know we have provided it at times on our own ourselves. So that's one of the reasons that these sand classifying tanks just can't be replaced. They fit a requirement that nothing else fits. And if you were to try to do the same thing with a different equipment, you'd be doing multiple stages and multiple pieces of equipment, and cost-wise, it just wouldn't be effective. So as Kurt mentioned, we're here to take some questions. If you have any, type them in the chat. I think I see one right here. Can you use a dewatering screen for a specification of a 0.5 millimeter to 1.5 millimeter sand? If you're trying to dewater that, yes, you can. If you're trying to make a cut point at the 0.5 millimeters, it's not going to make a sharp cut point, because that's not what a dewatering screen is necessarily set up to do. I see another question here. The air going up to the cyclone is created by a vacuum pump? No, that it's created by nature itself, by the centrifugal force of the material swirling around, much like a tornado. It's just pulling the air up because it creates a lower pressure point in the middle. So nature abhors a void. So the void happens within the middle of the cyclone itself, and it pulls the air up into it. So it's not a vacuum pump or anything like that. There's no additional thing to it. It does it by itself just off of physics. Okay, if there's no more questions on this, I'd like to thank you for everybody being here. Hopefully we've been of a service to you and provided some good information to you. Thank you for your time.
Thank you, everyone.